16.3 is a real important one. We're going to just work through a lot of acid-base related ice tables. There's nothing tricky to it. It's just going to be a matter of doing the work. Okay, so we have first finding the pH of a 1.5 formal solution of ammonia. So we'll write the chemical equation here, NH3 plus H2O in equilibrium with NH4 plus and OH minus. And we can do the ice table. And I'm going to do this really rapidly because these ice tables all look alike. And hopefully by now you're starting to have some intuition about what the equilibrium expression will look like at the end. But we'll go through all the steps, we'll just do it quickly. So we have 1.5 and 0 and 0, minus x plus x plus x, 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 1.5 minus x. Now we look up the Kb value for NH3, and that is 1.8 times 10 to the negative fifth, and that is going to equal x squared over 1.5 minus x. We will assume that this x here is small, and so we can just ignore it. And x is going to equal the square root of 1.8 times 10 to the negative fifth times 1.5. And when we do that, we get a value of x is equal to 5.196 times 10 to the negative third. And that is certainly small relative to the 1.5. And so that assumption was fine. And that is equal to our OH minus concentration. Right? X is the OH minus concentration. And so 5.196 times 10 to the negative third molar is our hydroxide concentration. Now if we want to find the pH, there are a number of different ways to do this. I showed you in the lecture what I think is a neat, quick way to combine some steps where we say pH is equal to 14 plus the base 10 log of this. But I'll just solve it a little bit more traditionally here. So we have H3O plus concentration is going to equal 10 to the negative 14th, that's Kw, divided by the OH concentration, 5.196 times 10 to the negative third. And so that's going to give us 1.925 times 10 to the negative 12th. And then we'll take the negative log of that to get our pH. In the end, we get a pH equal to 11.72. Okay? Now the next one is a 0.25 formal hydrofluoric acid. So HF plus H2O in equilibrium with H3O plus and F minus. Here we have our ice table. And what was it? 0.25 formal. So 0.25, 0 and 0, minus x plus x plus x. 0.25 minus x is the equilibrium concentration of HF. And then x is the equilibrium concentration of both H3O plus and F minus. We'll look up the Ka value for HF, and it's 6.6 times 10 to the negative fourth. That should equal x squared over 0.25 minus x. And as usual, we will hope that this is small, although we've got a couple of indications that it's not going to be quite as easy of a call this time. So 6.6 times 10 to the negative fourth, That's more than halfway toward 10 to the negative third. That's a decently large value for Ka. And then 0.25 is maybe kind of a smaller concentration than some of the others we've looked at so far. So we'll proceed with our hearts full of hope that x will be smaller than 5% of 0.25. And we get 0.0128, and this is 5.14% of 0.25. It is just barely too large. And that means that we really should go back and solve this equation using the quadratic formula. Now, I showed you quadratic formula in chapter 15, and I wanted to show you an alternative way to solve these sorts of problems here in the quiz. But I have misplaced my calculator, so I'll pause this and be right back. Okay, let's see how this goes. If you don't want to solve the quadratic formula, and you don't have access to a tool like Wolfram Alpha, where I showed you it can use a computer algebra system to solve for unknown variables and equations, like for example on an exam where the only tool you should have is your calculator, then I'm going to show you a way to get a numerical approximation of the answer on your calculator. Now, unfortunately, I have an HP calculator instead of a TI, so I will try to draw attention to how it'll be different for you than it is for me, but the process is essentially the same. What we're going to do is graph both sides of the equation as if it is a line. And the equation I mean, this is going to give you vertigo, but I'll just quickly point it back at the board. Whoop. Wrong way. Okay. That is the equation. 6.6 times 10 to the negative fourth is one side of the equation. And x squared over 0.25 minus x is the other side of the equation. Okay, so we're going to graph those sides as two different lines. And the place where they intersect, that is going to be the solution to this equation, or in other words, it will give us the value of x. Okay, I've rearranged things a bit. Maybe this will be a little bit better. So your TI calculator is going to be different than my HP calculator, but here in this corner right here, you should have a button that will get you to where you can input some functions. Y equals some function of x. So for me, it's a button press here, and I'm going to have to add equations. You won't have to do that. You'll already have y1 equals y2 equals, etc. But anyway, here we go. y1 is equal to 6.6 times 10 to the negative fourth, and I'll input that function. And then I'll add another one. y2 is going to equal x squared divided by 0.25 minus x. Okay, now I've got my two functions in there, and we can get ready to graph this. Now, if I go to the window, I can see that I've got default values of x ranging from about -6 to +6, and y ranging from about -3.2 to +3.2. On the TIs, those default values are -10 to +10 for both. And you could probably use those numbers and get away with it, but let's go ahead and choose some reasonable bounds for both our x range and our y range. We know that we have 0.25 minus x in the denominator, and so x should be bounded, you know, at the very least from 0.25, from 0, it needs to be a positive value, to the very most of 0.25. So let's go ahead and do that. We'll we'll put 0 there as my x min and 0.25 as the x max. And then the y values, if we think about our first function, y is equal to 6.6 times 10 to the negative fourth, well, that's a constant. That will be just a straight line. So let's just have our min be 6 times 10 to the negative fourth, and our max be 7 times 10 to the negative fourth. And 6.6 times 10 to the negative fourth should be a horizontal line right in the middle of our graph. Now, for my calculator, I'm going to erase and then draw. You can just go to graph. And, oh, hold up. This is a my calculator problem, so I'm going to pause it and solve it. I'll be right back. Okay, sorry, that's fixed. We'll go to draw. And it's being a bit slow, but you can see now there's a vertical line. That's the right side of the graph, x squared over 0.25 minus x. And then there's the horizontal line. That's 6.6 times 10 to the negative fourth. Now, on your TIs, I believe you have around here a button that says Calc. You can click on that button. I'm going to hit the function button. And you'll get a new menu. And on the TIs, you'll look for the intersect button on that menu. I have it right here. And then on the TI, I believe you're going to have to select the functions that you want to see the intersection between, especially if you have many functions there in your y equals menu, then you're going to have to use the up and down arrows to navigate and make sure you're selecting the two functions. So you'll hit enter for the first function, enter for the second function, and then it will ask you for a guess. And the point of that is that there may be more than one intersection, and so you just move your cursor over close to the intersection that you're interested in. In this case, we only have one intersection on screen. And so my calculator did all of that kind of automatically, but if you're on a TI, after you hit the intersect button, you usually just hit enter 3 times, and you don't even have to think about it if you've got it set up with only 2 functions and with a window that will have only one intersection. You can just hit enter 3 times and it will give you the answer. And in this case, I've got the answer down here, 1.251947 times 10 to the negative second. So about 1.25 times 10 to the negative second. Now, our simplified formula where we ignored the value of x gave us 1.28 times 10 to the negative second. And so with 3 sig figs, that's certainly a significant difference. With only 2 sig figs, we probably could have gotten away with not doing this graphical solve. But with 3 sig figs, we definitely would need to do this. And I just thought it was a good opportunity to show you how to use your calculator to find a solution. Now that is not an algebraic solution. If you were to take the quadratic formula, you may find that it deviates from the number that your calculator gives you, but that deviation would be like down in the 8th to 10th significant digit. Your calculator is able to make a very, very close approximation through this graphical method. And it's certainly close enough, and it's a whole lot easier than actually solving the quadratic equation. So I wanted to demonstrate that for you, and this problem seemed like a great opportunity. So we've got our number now. X is actually 1.25 times 10 to the negative second. So now we can come back here and say x is actually equal to 0.0125, and x is our H3O plus concentration, and so the pH is just going to equal the negative log of x, and that's going to be a pH of 1.90. We only get 2 sig figs in the end, so that is the solution. Let's move on to the next one. Here we are. here we have malic acid. It is a diprotic acid. And so we're going to have 2 Ka values. And you can find those in your textbook. We have a 0.3 formal solution. And our Ka1 is equal to 4.0 times 10 to the negative fourth. And Ka2, so that should be a capital A, Ka2 is equal to 6.3 times 10 to the negative sixth. So again, 10 to the negative fourth, well, luckily this time it's a little bit less than halfway to 10 to the negative third. We have a little bit higher of a concentration, so I think we'll be okay not using the quadratic formula this time. Especially considering last time, with only 2 sig figs, we probably could have gotten away with it. And all the conditions here are slightly improved from there. Okay, so I'm going to write our 2 simultaneous ice tables. And to save space, and just to simplify it, I'll call malic acid H2A. And that will be in equilibrium with H plus HA minus. So that is our first ice table. Let's just solve that one right now. We start with 0.3 and 0 and 0, minus x plus x plus x, 0.3 minus x, x, and x. And Ka is 4.0 times 10 to the negative fourth, and that is equal to x squared over 0.3 minus x. We'll assume that this x is small, and that will allow us to solve for x without using the quadratic formula. X will be equal to the square root of Ka1 times our initial H2A concentration. So the square root of 4 times 10 to the negative fourth times 0.3. And this gives us a value of x, where are we? Equal to 1.10 times 10 to the negative second. And that is about 3.7% of our initial amount. This time we are below that 5% threshold, and we can move forward with confidence. And so let's go ahead and put those numbers where they belong now. So 0.3 minus 0.011, well, that ends up with 0.29, I'm sorry, 0.289 molar. That's 0.3 minus x. And then for x and x, we just have 1.10 times 10 to the negative second, 1.10 times 10 to the negative second. Only we know that the chemicals aren't done reacting yet. HA minus is itself a weak acid. And so we'll have a second ice table over here. HA minus in equilibrium with H plus plus A2 minus, the second protonation of malic acid. Okay, and now what is our initial concentration here? We'll take it from our first ice table, 1.10 times 10 to the negative second. And our initial amount of H plus this time isn't 0. We have quite a bit of H plus from that first step, 1.10 times 10 to the negative second. And A2 minus, this is 0. And just to make it so that it's not at all ambiguous, we'll use a different variable this time. We'll say minus y, plus y, and plus y. Y is just like x. It's just the unknown amount. Some amount of HA minus will dissociate into H plus and A minus. In the lecture, I just called this x. Here for the quiz, maybe it's a bit more clear if we give it a new name. This will be y. And here we get 1.10 times 10 to the negative second minus y. 1.10 times 10 to the negative second plus y, and y. Now, this all is the equilibrium governed by Ka2, and so we'll say 6.3 times 10 to the negative 6 is equal to 1.10 times 10 to the negative second plus y times y divided by 1.10 times 10 to the negative second minus y. Now if we assume y is small, it's going to be small in both of these cases, and so these y's will be ignored. And now these 1.10 times 10 to the negative seconds will cancel out, and what we end up with is y equal to the value of Ka2. And these will always simplify in this way, this type of problem. Your amount of change in the second step will just be equal to the K value for the second protonation. And so we can now put that value in 6.3 times 10 to the negative 6. Now, it's worth going back and looking at whether this small amount of reaction is going to affect our equilibrium position from the first step. And this is equivalent to asking, is 6.3 times 10 to the negative 6 small relative to these numbers? We could probably use that same 5% rule. And it is small. And so it's not going to upset the balance that was already established in that first step, which means these are all final numbers as well. Our malic acid concentration, 0.289 molar. Our hydronium concentration is 1.10 times 10 to the negative second molar, as is the HA minus concentration. And finally, our A2 minus concentration is 6.3 times 10 to the negative 6. And that leaves us just one last question: what is the pH? And so we'll just say pH is equal to the negative log of our H plus concentration, 1.10 times 10 to the negative second. And this should be 1.96. 1.959 is what I got. That rounds up to 1.96. That is the pH. And this problem is done. Okay, one more. Find the pH for a 1.5 formal solution of sodium hypochlorite. Now this is an ionic compound, so we're going to have to look at both the cation and the anion. We'll determine their acidity or basicity before we can do anything with the concentration and the numbers. We have sodium NaClO, sodium hypochlorite. This will break up into Na+, sodium, and ClO-, hypochlorite ion. Now sodium is neutral. Those group 1 and heavy group 2 metal cations are sort of the counter ion to soluble hydroxide salts, and they are neutral. ClO- is a part of the hypochlorous acid hypochlorite conjugate acid-base pair. And so we can look up the Ka value for HClO. That's 4.0 times 10 to the negative 8th, according to the table in the appendix of your textbook. And so the Kb is equal to Kw divided by that value. And I'll just write the solution up here because we'll need it for the next step. Kb is equal to 2.5 times 10 to the negative 7th. And now we know it's going to be a base, and we've got a value for that base dissociation constant. And we can now treat this like a regular ice table type problem. We'll have ClO minus plus water in equilibrium with H, ClO plus hydroxide. Here's our ice table. And we're going to start with 1.5 formal solution of the sodium hypochlorite. There's no subscripts to that sodium hypochlorite to suggest that the hypochlorite ion concentration is any different than 1.5 formal. So we have 1.5 formal. And what I mean by that is if it had been magnesium hypochlorite, then we would have had MgClO2, right? That 2 in the case of magnesium hypochlorite would be very important because it would mean we have 2 hypochlorite ions for every 1 formula unit. But we don't have magnesium hypochlorite, so we can just take the 1.5 and we'll say 0 and 0. Negative x plus x plus x, x, 1.5 minus x, and we'll have that Kb value 2.5 times 10 to the negative 7th is equal to x squared over 1.5 minus x. Is x going to be really small? Yes, it is. So we can just say that over 1.5. And we'll solve this to get a value of x equal to 6.12 times 10 to the negative 4th. That's the square root of Kb times 1.5. And this is the OH minus concentration, and so the pH is going to equal 14 plus the log of x. Because the OH minus concentration, taking the negative log of that would give us the POH, and then the pH is equal to 14 minus the POH, and the 14 minus the negative log of x turns that into a plus. So 14 plus the log of x gives us a pH of 10.79. Okay, so I think this is a really important quiz. If you need to go back and rewatch any portions of this, make sure you understand how to solve these types of equilibrium problems. I told you we'd be looking at equilibrium and ice tables a lot, and this is still not the end of it. And so make sure that you've mastered these skills, because we'll move on and build on these ideas even more in Chapter 17.